Okay, so here we are with our second installment on gravitation. We've completed the Newtonian portion of gravitation, and now we're moving into the modern physics or the Einsteinian portion of gravitation. So we begin with number 5, which is special relativity. And it states that moving clocks run slow. So let's investigate this a little bit. This is a picture of Einstein in 1905, and this is a picture of Einstein in 1930. In 1905, Einstein was working as working at the patent office on the third floor in Switzerland, and he had a little extra time on his hand. And so, what do you do when you have a little extra time on your hand? You tend to daydream. So he asked himself some important questions about the universe. And he came up with this idea of space-time. And so what he's going to say is basically you have space and you have time, and it's one entity or a fabric. So if you can alter your space enough, the result is time will slow down. Now you won't have any idea that time is slowing down. This happens in such a way that even your brain or your processing skills slow down. So to you it just feels like an average normal day, but to someone on the outside looking in, they will see immediately that you have a much different time than normal. One of the things we talk about in class is the light clock and how we can use the light clock to explain special relativity to people. So the outcomes of special relativity is something called the twin paradox. So the twin paradox basically explains how we can have two identical twins. One leaves close to the speed of light. One stays put. The one that's traveling at the speed of light has a different time than the person who stays put. So that when you come back, you experience a dilation. The twin who traveled close to the speed of light is only aged maybe 5 years, but the person who stayed on Earth is much, much older, maybe even up to 100 years, depending on how close you get to the speed of light. So that's the twin paradox. Einstein's second portion of relativity deals with the same fabric that he mentioned earlier. So he's looking more specifically at accelerated motion. So he has an idea that mass can even bend light. And then this theory he has is proven the very next year. So what they do is they go to Africa to kind of see where there's a solar eclipse, and when they look at the solar eclipse, they realize that the stars' positions aren't really where they're supposed to be. And what's going on is that as the light from the star nears the sun, it causes the light to bend, and so people on Earth see it in a different place than it should be. And this was enough proof for people to kind of buy into the idea of general relativity. Later we found out some other things that deal with it. For example, black holes. Black holes are of course black. You can't really see them in the night sky with a telescope. You have to use special equipment, radio waves, X-rays, that will penetrate through some of these other objects in space and pick up this energy that's being released by the black hole. So the black hole will shoot two plumes of energy up and above and below, and then it also has something called accretion disk on the outside. And these two things can be seen in the X-ray, and if we use the X-ray telescope, we can kind of find these things in the night sky. What pertains to general relativity is the idea of gravitational lensing. So if we do have a black hole in between us and, let's say, a star, what can happen is as the light leaves the star and goes toward the Earth, you start to see that that star is going to be positioned in more places than once. In fact, this is called Einstein's cross, and this is a good representation of mass bending light or gravitational lensing. Not to worry though about a black hole, because even if our own sun would become a black hole, of course it's not massive enough to become a black hole, but even if it did, we would still continue to orbit that sun as we are past what they call the event horizon. So lights would go out, but we wouldn't necessarily be pulled into the black hole. Here are some different sites that you can check out if you want to see some different videos on black holes and general relativity. And then this is a nice site on relativity in general. You can go through there and do a tutorial and try to learn more that way. And then this last site kind of ties this entire chart all together. So that's it for gravitation.